There are instructions for the examples. So let me first quickly show you what we are going to do with the first example. As I said, is the example is internal measure. It's a very simple model, but it's actual project we are working on for near-surface geophysics. The model is from near-surface geophysics for void detections. So this is in collaboration with military. We want to detect the voids using spectral elements like tunnels for traffic drops and for the military purposes. But yeah, the idea behind is quite intriguing, but the model is really simple, and you'll see that this simple model already allows accurately reproduce the data, observed data on the ground. So this is the layout from the actual survey for the experiment, for this prototype experiment, where you have in blue line the receivers, geophones, 10 lines of geophones recording vertical component of velocity, and also the sources, so quite dense array of receivers and sources. And if you want to detect, like say, if we is it possible using SPECFEM and imaging, joint seismic imaging, to detect the voids, which, like we know a priori, the tunnel should be about this area, about 10 meters depth, and the size of the tunnel is like 1 by 2 meters. So this is the layout. So this is the mesh we will generate. Pretty simple. You see the geometry, there is no variation in topography. It's flat. So the mesh is regular on the near part on the surface, and there is only one like observation is it's slightly stretched at the bottom, just to gain a little bit of performance. But in general, it's not a good advice, I think, to stretch the elements. The ratio 1:1 is good. But this is the mesh we'll generate. This is again the slice of the mesh, vertical. And at the second step of the workflow, the SPECFEM, because we use internal measure, will interpolate the values, velocities. Here is VP model to that mesh. So you see the P-by velocities differs from about 500 meters per second to 1200 meters per second. So low at the surface and then getting faster. The mesh is overlaid with the velocity model at the step 2. And we'll look at the seismograms. So this is the shot gather. There are 72 traces on the both pictures, on the left and on the right side. So the receivers aligned. This is one line of receivers for one source. On the left side, it's observed data at given frequency range between mostly between 4 and 40 hertz. The signal is filtered to this frequency. So you see, this is the data we have, and this is the seismograms from the SPECFEM. Well, okay, good or not? Not good at this level, at this frequency range. We go to the lower frequency scale from 4 to 28 hertz. It's more, the match is better. So basically, this is some first arrivals here, and this is surface waves, and this is the surface waves in the synthetics. And if you go at the lower scale, you see how the data now compare to the observations. The one thing is that the polarity is flipped in the synthetics. You can see at 0.1 the blue color here, whereas the red in the observations. But this easily because the polarity of the source was not good at this point, but the match is really nice. And actually, at this frequency, we can already see the tunnel, the signature of the tunnel. So this very weak signal, backscattering, the waves going, it's very difficult to observe at this level, but this is the signature of the tunnel, of the voids. So we can already see it from the data. But we performed imaging and we have some preliminary results. So given this simple model and applying the conventional strategy going from the low frequency to high frequency, we're able to detect the void. So now we'll make this, simulate the wave in this model. Before, just the same comparison of the traces, synthetic traces and observations at 3 different receivers. So at near, middle, and far offset. So the offset is the distance between the source and the receiver. So at this, again, at the high frequency range, it's not good. It's better at this frequency range. And that's at low frequency what we have. So the match is really nice. Now, so let's go to the example. So first of all, we need to download the prepared examples from GitHub. So I put every examples to GitHub. So if you can, sorry, I didn't put this in the instructions, the very first step, but the next steps would be in the instructions in that folder. So we need to git clone. If you can type this. So we haven't tried to run these examples on the virtual machine, but we'll try now. So the instructions open here. We can skip this connection to the Peloton, to the local cluster, and loading these modules should be there in the system. First of all, we need to download the SPECFEM3D. So we will work with the Cartesian version. So use this command to download the binary, the source code for the SPECFEM. The software 2D or SPECFEM3D is already downloaded and configured through these commands. So this is particular for Peloton system. So we configure SPECFEM for, yeah?
It's the master branch that's impacted to SPECFEM3D. If you go to git fetch, git checkout, develop, then you can be on the develop.
Oh, it's the master branch? Okay. Doesn't matter, we can work with the... Yeah, any reason why not work with the master branch? Well, I'm used to work with the development, but there could be some inconsistencies, yes.
Perhaps we can guide them to
How to
switch to the develop branch.
Okay.
So, all right, so if everyone can navigate to the SPECFEM 3D directory. Packages. Underneath packages. And now do a git fetch.
So if development is fine, you don't need to worry about.
Once that command finishes, then type in git checkout develop. So,
The output should be master. The output should be master.
Develop.
there we go. So the command is git checkout devel. And now if you do git branch, the star should be next to devel, which is highlighted in green. So that means you are now on the development branch. So everyone is at that point.
So we need to generate binaries, configure the SPECFEM3D. So we go to the SPECFEM3D directory, you download, and for this system you configure with this line, command line. So we configure using this line and to generate binaries, this make all. Yeah, so for this, there is a mistake, as there is discussion. There should be a $sign here. It's a separate command in that line, just to specify number of cores to at the step of compiling the SPECFEM. It's not the number of cores we will use for the simulation, just to speed up this process of the SPECFEM installation. So then you type make all, and you should be able to create binary files inside SPECFEM3D binary. So you have these subcommands, and we will use, in the first example, we will use xMeshFEM3D to build the mesh, internal mesher. Then xgenerate database at step 2, and also to run the solver, this